Let us talk about this problem. We are given a number n. We need to print all divisors of this number n in increasing order. For example, number is 15. Its divisors are 1, 3, 5 and 15. These are the numbers that equally divide 15. If number is 100, then we have output as 1, 2, 4, 5, 10, 20, 25, 50, 100. These are the numbers that divide 100. And 7, when you have prime numbers, you are going to have only two divisors, 1 and 7 itself. Now please pause this video and try to write down a function that takes a number n as input and prints all its divisors in sorted order. Let us first talk about a naive solution to solve the problem. The idea is simple. Our divisors can range from 1 to n. So we run a loop from 1 to n, and for every number I, we check if I divides n. If I divides n, we print I. So if n is 6, we are going to run the loop from I equal to 1 and 1 divides 6. So we are going to print 1 on the screen. I is 2, then 2 divides 6, we are going to print 2. For 3, we are also going to print. For 4, 4 does not divide 6. 5 also does not divide 6. So we are not going to print anything for these. 6 divides 6. So we are going to print 6 and we are going to stop at 6. See, I have written here print. It's kind of pseudo code. If you're programming in C++, you can replace this print with cout. If you're programming in Java, you can replace it with system.out.print. Let us now talk about time complexity of this solution. This solution simply runs a loop that runs n times. So our time complexity is clearly theta n. This solution is going to take theta n time and theta 1 auxiliary space. Now please pause this video and try to think of a solution that works in time complexity less than theta n and theta 1 auxiliary space. To give you a hint, your solution is going to take theta of square root of n time. The efficient solution that we are going to talk about is based on these two facts. The first fact is divisors of a number always appear in pairs. For example, if you see 30, the two divisors 1 and 30, they multiply together and make 30, right? And they form a pair. So every pair of divisors is formed in this way, that the two numbers in pair multiply together form the number 30. So 2 and 15, it's a pair, they together make 30. 3 and 10, when you multiply 3 and 10, you get 30. 5 and 6, when you multiply 5 and 6, you get 30. See, when you have perfect squares like 25, then you have a pair where you have the same number repeating 2 times, right? But you still have a pair. Now, one more interesting thing about these pairs is one of the divisors in the pair should be smaller than or equal to square root of n. And how is this true? See, you have a pair xy and x into y is n, right? We can see here above. And let x be the smaller of 2. You can pick any of these two as smaller than the other, right? Smaller or equal to the other. In case of perfect squares, you may have equal values as well. So let x is smaller than equal to y. Then we can write x into x is smaller than or equal to n. So I have replaced y with a number which is smaller than or equal to y. So I have to put this sign, right? From this I can conclude x is smaller than or equal to square root of n. So we can say there is always a divisor which is smaller than or equal to square root of n among all the pairs. What it means is, if I traverse from 1 to square root of n, I will find at least one divisor in every pair, right? Because one divisor has to be smaller than or equal to square root of n. So for example, if I take 30, 30's square root is going to be 5. If I take the floor of a square root, right, it will be something like 5 point something. So if I traverse from 1 to 5, I'll find one divisor among all the pairs. So 1 is there, 2 is there, it's smaller than 5, 3 is also smaller than 5, this is equal to 5. So I can find one divisor in every pair. Now try to use this idea and try to print all the divisors of a number in time complexity square root of n. Here is implementation of the ideas that we just discussed. This is a simple implementation. It prints all divisors, may not print in the required order, which is the sorted order. Let's first take a look at this implementation, then we'll implement the idea with all the divisors in sorted order. So what we do here, we run a loop from 1 to square root of n, because we'll find one divisor of every pair with this, and we'll print the divisor and then we'll print the other divisor by printing n by I. That way we get all the divisors. So we run a loop from 1 to square root of n, and instead of computing square root of n, we have done this way. I into I should be smaller than or equal to n. So this is basically going to run till square root of n. And for every I, we check if n is divisible by I. If n is divisible by I, then we print I. And we have this condition which says that if I is not equal to n by I, then only print n by I. So what does this condition mean? See, in case of perfect squares like 25, what will happen? When I becomes 5, you will print 5, but you don't want to print 5 two times, right? So for those cases, we have this if condition. Let's see how does this code run for 25. For 25, we are going to run from 1 to 5. When you run for 1 is dividing n, right? So you are going to print 1. Then this is not true. 25 by 1 is 25 and 25 is not equal to 1. So we'll come here and we'll print n by I, which is 25. Right? Now we'll run for I equal to 2. When you run for I equal to 2, n is not divisible by I. So you will not go inside this if condition. Same is the case with 3 and 4. You will not go inside the if condition. When you come for I equal to 5, you are going to go inside this condition. You are going to print 5 and you are not going to print this n by I because I is equal to n by I, and we are going to print only when it's not equal. 5 is equal to 25 by 5. So we'll print only 5. That way we get all the divisors of 25. The divisors are 1, 25 and 5. But we do not get these divisors in the sorted order. So please pause this video and try to modify or extend the solution so that it prints all the divisors in sorted order. Please note that the time complexity of the solution is square root of n, and we want to keep the time complexity as square root of n only, and we want to print all the divisors in sorted order. Let us now see the efficient solution that works in theta square root of n time and prints all the divisors in sorted order. The idea is to traverse the numbers from 1 to square root of n 2 times. First we traverse from 1 to square root of n and we print all the divisors in this range. Then we traverse from square root of n to 1 and then we print the divisors of n by I form for every number I. So this way you get all the smaller divisors first and then all the greater divisors. So we have 2 loops. The first loop prints all the divisors from 1 to square root of n. 1 is inclusive and the square root of n is exclusive. Which means if a number is a perfect square like 100, then the first loop is not going to print 10, right? The second loop begins with the square root of n and goes till n, and it prints all the divisors in the range from square root of n to n. Let's now see how does this code work for n equal to 15. When n is 15, we are going to run this loop from 1 to 3, right? Because when I becomes 4, 4 into 4 is greater than 15. So we'll stop at I equal to 4. So what happens from 1 to 3? When you run for I equal to 1, 1 divides 15, so you are going to print 1. Then 2 does not divide, so you are not going to print 2. 3 divides 15, so you are going to print 3. So you get 1 and 3 on the screen. And then you stop this loop. So when you stop this loop, your I is 4, right? You stopped because 4 into 4 was greater than 15. Now you begin this loop with I equal to 4. There is no initialization here. We begin with whatever is the current value of I, and we run this loop while I is greater than or equal to 1. So you begin with I equal to 4. 4 does not divide 15, so you will not do anything. Now you come to 3. Here we are decreasing the loop. When you come to 3, 3 divides 15. But this time we do not print 3, we print 5. So we print n by I, right? So we print 5 here. Now we come to 2, we decrease the value, right? And 2 does not divide, so we will not do anything. Now we'll come to 1 and 1 divides 15. So we are going to print 15 by 1, which is 15. This way we get all the divisors in the sorted order. Now what is the time complexity of the solution? This loop runs theta square root of n times. This loop also runs theta square root of n times. Theta square root of n plus theta square root of n is theta square root of n, and it requires theta of 1 auxiliary space.